Okay, so the last lecture was an introduction to certain methods whose main use was going to be for the discussion of networks of qubits. And as I explained last time, this encompasses a very large number of physical systems, both constructed by nature and also by us. And in particular, I told you a little bit about the applications in biology, and I'll say a little bit more about that today. One thing I didn't mention, of course, is the application to astrophysical systems, but I'm not going to have time for that. Okay, so no, that's the wrong one. Of course, it's not working because there's no. Okay, so I'll just do it manually. All right, so so these were some of the systems that I mentioned last time in the context of spin networks, everything from certain kinds of graph to biological systems. So let me now say what I'm going to do in this lecture. Now, in this lecture, I've actually put a lot of material which I'm not going to discuss very much during the lecture. It's there if people want to read it. In particular, there's rather dense theory, which basically theorists prefer to look at in their own office anyway, and experimentalists usually don't want to look at it at all. So I'll just simply indicate what it's all about and then pass on. So I'm going to discuss the following questions. This certainly does work. First of all, I'm going to come back again to the question of which networks are important. And the main question that we're interested in is not things like their thermodynamics, statistical mechanics, which is the thing that condensed matter physicists are interested in. We're interested in their dynamics, which is in fact a much more complicated question usually. And one of the reasons we're trying to do this is because we want to understand quantum computation. And of course, we want to know how we can deal with this experimentally. And so as in the previous lectures, I will be discussing some real-world examples in the later part of the talk. Okay. So let me just remind you of some of the real-world examples that one is interested in. Gated quantum computers. This is an example of a quantum icing system. This is another example of a quantum icing system, but now in one dimension. This is an example of a model which can be mapped to a quantum icing system. It's the ring molecules that exist inside a light harvesting molecule. And then here are some ideas for quantum computation. This one is the one favored by some people working in magnetism. It uses the phthalocyanine molecule. And this is not a quantum computer, it's the quantum annealing system used by D-Wave, which is sometimes called an adiabatic quantum computer. Okay, so the models that we're interested in, what are they? Well, as I explained to you last time, one can always map between three kinds of model. One is a lattice of spins. One is a model which is called a quantum walk, in which a particle hops around on some graph. And one is a model of the type here, a spin model. It's fairly obvious, I think, that you can map between a model of quantum gates and a spin model. It's less obvious that you can always map to a hopping model or a quantum walk. The surprise actually is, of course, that the quantum walk is more general than the network of qubits or spins. This certainly surprised me when we did the mapping. So in fact, there are many models of quantum walks which don't have a corresponding quantum information processing system, but the converse is not true. The simplest kind of quantum walk that people discuss is of this kind. This is where an object hops from one site to another and some phase is accumulated, and that these energies of the different sites are different. And the key ingredient that I'm going to be adding here is, of course, this coupling to an environment. Actually, we discussed a more general model of this kind in which there's an operator on each site. And if you want to think about what this might be, you could imagine we attach some spin of magnitude s to each site, but it could be more complicated than that. Which is also switched on and off when the particle is on that site, and likewise on each link. And then there will be some Hamiltonian describing the dynamics of these variables on the sites and the links. And it's also actually useful to know that you can always write some dual transformation in which you map sites to links and links to sites. Okay. So, and in fact, one of the nice things about this is that you can use these extra variables to create new nodes and links. And in this way, you can generate a network that grows with time, depending on its time evolution. This is, of course, highly nonlinear, but it's very interesting if you're trying to do the sort of thing that I was talking about in the first lecture, which is autocatalysis, in which you generate new networks which then feed back on the originals. An example, a very simple example of a spin system is, of course, the quantum Ising system. This is where we have transverse fields on each site, and then we have longitudinal interactions only between the spins on different sites. Of course, one is often interested in adding transverse fields, but I'm not going to discuss that. Okay, so I've already discussed this model and this model a little bit without the environment. So, of course, very important question is what happens when we add an environment. And as we've been discussing, there are two important environments that one deals with. One is where you couple the system, and I'm going to discuss this now for quantum walks because it's easiest to do so, but one can, of course, do the same for spins or for quantum gate networks. In one case, you couple this to a set of oscillators. So this could be photons or phonons or spinons or holons or any number of other bosonic excitations which are delocalized. And then you will have either a diagonal coupling in which, this is the diagonal coupling in which the interaction between the boson and the particle only happens when it's on a particular site, or a non-diagonal one in which it happens when it's hopping. In other words, we have interactions between the particle and the bath when it's either on a site or on a link. And if you only consider linear interactions to the oscillators, then this is the most general interaction you can write down. I can, of course, allow it to interact with the momentum of the oscillators as well. But if I do that, I can always make a canonical transformation to bring it back just to the position operators. So this is the kind of interaction that you would have with an oscillator bath. In the case of a spin bath, well, I'm choosing two-level systems here, so I have a set of Pauli matrices for each of the bath spins, and there will be some local field on this. In reality, as I explained, these could be defects, they could be electric or magnetic objects, they could be nuclear spins, paramagnetic impurities, and so on. There are many such excitations. There will be interactions between them. Typically, these are weak because these objects typically represent localized modes rather than delocalized things like phonons or photons. And again, one can write down the most general interaction, and again, it either involves links or nodes. If you want to write things in terms of spins rather than quantum walks, then again, well, this shows the interaction between a quantum Ising spin system with spins tau and a set of sigmas which represent the bath spins. And here we have the most general coupling. It's a tensor coupling to the spin bath, and then these would be the interactions between the spins and the oscillators. And here I'm showing interactions to both the position coordinate and the momentum coordinate of the oscillator bath. Okay, so these are the general interactions that one deals with. And last time I discussed the behavior of a single qubit coupled to either a spin bath or an oscillator bath, and we saw that it could be very surprising depending on what particular model we had. So of course, now we want to look at the more general lattice. Now, this is part of the section that I'm saying that this is for people to read if they want to. Perhaps they don't. But the question is, how does one attack a problem like this? Because you already saw that when we attack a problem of a central spin coupled to a bath, things can get very complicated when there are long-time memory effects in the interaction. So you could imagine that it can get extraordinarily complicated when you have some general network. And that's true. So let me just give you an idea of what one does. I think many of you will probably have heard of the BBGKY hierarchy. This is Bogolyubov, Born, Green, Kirkwood, and Yvon. And what they did was they started from this is now for a classical gas or fluid. They started with the n-particle density matrix of the system. Well, actually, sorry, this is a classical system, so it's just the probability distribution function. And then you integrate out some of the coordinates to get a reduced distribution function here. So this is a function of n position variables. This is a function of only s. And then you ask, what is the time dependence of this object? Well, one divides out a factor of volume, and this is the famous BBGKY equation, which is a horrible integral differential equation which connects the dynamics of different level distributions. So we see on the left here we have S, but on the right here we have S plus 1. And this is what you would expect. And the simplest example of this that one knows is the Boltzmann equation. This connects the one particle distribution and its time and spatial dependence, this is essentially the total time derivative, with an integral over the two particle distribution, which of course contains collisions. And this is the lowest member of this hierarchy. And one does exactly the same for quantum mechanical systems, or indeed for quantum fields. And again, I'm not going to go through the algebra, it's horrible. And in fact, most of the time, if you're a theorist, you don't even bother to write down all the equations, you simply look at the diagrams. So this is the equation for the nth correlation function, written in terms of the n plus 2th correlation and the nth with an integral over it. And the lowest member of this is, in fact, well-known Dyson's equation, which relates the 2-particle green function to the 4-particle green function. And this is the precise analog of Boltzmann's equation. Now, we're interested in qubits, or hopping particles, and so we have to do all of this for spins, which, curiously enough, has not really been studied much in the literature, and it gets very complicated, and I don't want to discuss the details, but this is the sort of thing that you need to use. Now, one of the interesting things about quantum computation is that, in distinction to almost every other field of physics, you don't just stop at 2-particle or 2-spin, or maybe 3-spin or 3-particle correlations, because you're interested in entanglement at the level of n qubits. And so if you really want to understand the dynamics, you have to look at all of them. And in fact, it turns out that you can write down, eventually, 2 to the power n minus 1 measures of the different kinds of entanglement in this system using all of this and their time dynamics. It's rather complicated, but it's the first time, as far as I know, that there has been an unambiguous definition of all the different kinds of entanglement in a n-qubit system. But it's very complicated, so I won't discuss it. A simpler example is where you're dealing with the hopping particle, the quantum walk. So let me again take this model that I showed you. So we have a particle, and in this case, I'm going to make it move around a ring. So you should just think of a ring of sites. And here I'm making it really simple. They just hop. Every site has the same energy. And I'm imagining that there's some flux phi going through the ring. So this is this classic Aharonov-Bohm problem. We have a particle moving around a ring, hopping from one site to the next, but there's a phase enclosed by the ring. And there it's very easy, it turns out, to solve analytically for the dynamics of the one particle density matrix. This is the propagator for the density matrix, and this is density matrix written in sight representation. And the propagator here, when you couple to an environment, has this object here, which can be calculated analytically, and this is the propagator for the particle's density matrix without a bath. And this function here is valuable analytically both for an oscillator bath and a spin bath. And so one can actually get exact answers for a system like this. This shows the enormous value of the mapping between a qubit system and a quantum walk, because to solve equations like this is not simple. So I want to show you an example of the kind of problem that one attacks with this kind of method. So this is a cute model. For reasons that will become obvious, we call this the capricious voter model. And there's actually a rather good example going on in the US these days. So officially, this is the quantum Ising system with a coupling to an environment. And what I'm going to show you is the time evolution of this system in the presence of long-range dipolar interactions between the spins on this lattice here. So this is actually the result of doing the analytic calculations and integrating out the environment on a lattice here, which was 32 by 32. So the results are not numerical, but I'm simply showing them at different times. And they turn out to be fascinating, as we'll see. So what I'm doing here is I'm starting off with a set of spins which are just oriented randomly. We've put down a completely random set of spins which are either up or down. And then we evolve it according to the quantum Ising system. So we have this transverse field, which of course is going to try and flip the spins. And we have these longitudinal Ising interactions, which are in fact trying to block that. And if you want to think about this in a simple way, the only way that the spins can flip is if the net longitudinal field of all of the spins on one particular spin is actually smaller, or of the same order, or smaller than delta. If it's large, then they're completely off resonance, and the transverse field can't flip them. So essentially what is happening here is that only the pairs of spins that are in near resonant coupling can flip. So this is fairly simple physics. And so it also means, of course, that they'll flip in pairs. And because these interactions are long range, this pair flip process will not necessarily involve nearest neighbors. And this is being done in 2 dimensions, which turns out to be the critical dimension of this system. Okay, so let's start and see what happens. Oh, that's right, it doesn't work. Okay, so this is after 1 time unit. That means a time of order 1 over delta. And we see that 8 spins are flipped. These, and these. You go a little further, more are flipped. And notice that there are 2 processes that involve 2 spins that are very far apart. And this is because of the long-range interactions. And those of you who are interested in quantum computation should be asking about correlated errors here. And so on. This is after time 100. A longer time. You might ask, why is it slowing down? And the answer is, of course, that every time you flip a pair of spins, they're no longer in resonance. And now the system is waiting to find other spins in resonance. Now, it's not that you just immediately exhaust the pairs of spins that are in resonance, because when the spins flip, they change the field everywhere else until you'll bring some spins into resonance that were not before. But it's slower. And so the thing slows down. But that's not the only interesting thing about this. So this is after 10,000, and this is after 100,000. And so you might ask, well, how do things go in the end? Notice that there is some sort of spatial pattern developing here, and there's certainly a pattern developing in energy space, which I'm going to show you later in experiments. So as a function of time, this is what happens. And we actually get Lévy flights, which is what biologists call punctuated equilibrium. That is to say, there'll be long waiting periods, and then there'll be a whole bunch of spins that will flip. which is kind of interesting. In 2 dimensions, we never get localization in this problem. Whether or not you get localization, in other words, whether or not eventually the system stops relaxing, depends on the dimensionality. We get a patterns formation in both energy space and real space for the long-range interactions. And the reason why this describes capricious voters is because typically voters vote to some extent based on what their neighbors are doing. And long-range interactions means that they talk on the telephone or they watch TV. And so the capricious voters are the ones that happen to be in contact with people who can, 50% of their friends are going to vote one way and 50% are going to vote the other way, and so the net field is actually 0. So you should remember this model because we'll see that it actually operates in many natural systems. Here's another theoretical example. This is where we have a particle hopping between sites, and it turns out the energy of the sites is all the same, and the hopping matrix elements are the same. So this looks like a simple band Hamiltonian, except we've coupled to a spin bath. This describes what I explained to you last time, precessional decoherence. The bath spins precess in the field of the particle, and the angles through which they precess depend on the path of the particle, so the particle and the bath spins become entangled. So we can ask what's going to happen in this case. Let's ask ourselves first, what do we think will happen? Well, first of all, we can imagine that the bath is not even coupled to this hopping particle, so that these alphas are all 0, so we simply have a particle hopping round a ring. Or actually, this is a cubic hyperlattice in some number of dimensions d. Well, if the particle's free, then we simply expect ballistic motion, band motion. So it'll just move through the lattice with some mean velocity. And of course, you can calculate analytically the result, and you find that the amplitude for the particle to start off at some site, which I'll call 0, and then be found at that site at a later time, goes like 1 over time to the power d, where d is the dimension, and that the variance of the final position goes like t squared. Well, this is exactly what you would expect. It's moving at some velocity, so after a time t, it'll be roughly a distance proportional to t away from where it started. Hence this result for the variance. Now you say, well, if it's coupled to an environment, it's going to move diffusively over long times, which would mean that the rate at which it moves away from the origin now would be going like the square root of time. That's what we mean by diffusive motion. And that would actually be independent of the dimension. And so we have this result here. So the standard pointer basis picture of the effect of an environment on dynamics of a system moving through space says that, well, we'll get diffusive motion eventually, because we're coupling to the coordinate of the system. And it turns out that when you couple to most oscillator baths, that does eventually happen. But it does not happen with the spin bath. And in fact, these are results of analytic calculations for the Hamiltonian I just showed you. Let me just avoid all the formulas and just show you what you get. So this is showing us the probability that after some time, the particle will be found at a lattice site distance n away from the origin. Now this is a 3-dimensional lattice, so I'm multiplying by n squared so that we can really see the probability that it's gone a distance n after a time t. The black line here is what we would expect with ballistic motion. And it would have moved some distance away, but of course, because this is quantum mechanics, the wave packet will be spread out. This is what we get when we interact with a spin bath, and the key you should understand here is that I've actually made the coupling to the bath extremely strong. The dimensionless coupling is actually 100 for this calculation. And this is the extraordinary result. There's a part of the density matrix which is actually slowed down and in fact shows weak localization in the presence of the spin bath, but there's a part of it which is actually moving ballistically. Still, the fraction that moves ballistically depends on the dimension of the hypercube. we were so surprised by this result that we didn't even publish it for 10 years. And then I had two conversations, one with Duncan Holday and one with Tony Leggett, and they both came up with alternative derivations of the result, and so we decided that we would publish it. And then in the course of writing the paper, I finally figured out what was actually going on. And so anyway, that's the result. But the moral of this story is that the effect of a bath is not always to create classical dynamics. So we've seen two interesting surprises here already. One is that long-range interactions can generate patterns in this quantum relaxation. This we saw before in this capricious voter model. And for those who are interested in correlated errors, this turns out to be extremely important. It tells you that correlated errors are not something that you can easily get rid of with an error correction code. And here it shows the moral of this story is that the effect of a bath is not always to produce classical dynamics. And there's one other moral which I already described for you a little bit last time, and this is that spin baths and oscillator baths operate at different energy scales. Spin baths typically operate at low energies, and oscillator baths, because the density of states is higher at high energies, at least in 3 dimensions, operate at high energies. And so if we look at the operating frequency of a quantum information processing system, then we find that the decoherence from oscillator baths is at high energies and that for spin baths is at low energies. And there's this what I call a coherence window in between. And I already showed you that the coherence window for calculations for a real system last time, and we'll see it again in other real systems. These are calculations, for example, for a superconductor. And the low energy decoherence is caused by nuclear spins. It's also caused by defects, for example, in squid qubits, and defects in the junction. And the high energy decoherence is caused by coupling to electronic quasiparticles and to phonons. And you see the same, this is the energy and temperature units, and this is the decoherence rate. Okay. So, as I've done before, I'm now going to discuss some real-world examples. I'm going to see how this theory works when we apply it to certain real systems. And in fact, I've left half the lecture to do this. So I'm using less and less theory as these lectures go on. And I'm going to discuss 2 icing systems. These are both systems that have been, for which an enormous number of experimental papers have been written. And the reason is that you'll see why. And then finally, I'm going to discuss 1D polarons. But these are ones that actually move around in biological systems. But let me say first a few words about the important things about quantum icing systems. As I discussed before, there are many examples of these. People who work in quantum optics are interested in chains of ions with spins. So these tend to be one-dimensional quantum icing systems. People in condensed matter physics tend to be interested in 2-dimensional or 3-dimensional networks. But in any of these cases, the model that we'll be dealing with, which describes the experiments, is the following. We have a set of 2-level systems, or qubits. These are the icing spins on sites. And each one of them has a transverse field and a longitudinal field acting on it. So this is tau x and this is tau z. And then there'll be some interaction between these spins, which involves only their z components, and which in this case I'm going to be choosing to be dipolar because that turns out to be by far the most interesting. There are many experimental realizations of it. And it's interesting for many reasons, but one of them is the connection with correlated errors, because it's long range. It also, in condensed matter physics, leads to fascinating phase diagrams, quantum critical phenomena, and so on. And these will be coupled to nuclear spins and phonons. So we're going to ignore electrons because they tend to wash everything out. As I described for you last time, the coupling between a qubit and an electronic bath tends to localize the electron. The coupling is very strong at long times. So, now, as we'll see, the moment we add the bath, we add a third parameter. So, supposing I ignore the bath, and then I have essentially two parameters. One is this delta here. I'm going to assume that epsilon is 0 for the moment, which is the quantum fluctuation parameter. It's trying to flip the spins. And the other is the interaction, which is trying to block them, as I described before. So typically, if we want to go to a quantum regime where there is dynamics, we have to increase delta. And if we want to freeze the spins, we have to increase V. And so we find that in between, this is this plane here, there'll be a transition called a quantum phase transition between the two. And in fact, this was the original quantum phase transition that was first discussed in the 70s, the quantum icing system. In other words, if I start off with dipolar or any other kind of longitudinal interactions between the spins and I increase delta, which is typically done by applying a transverse field, eventually I'll get a quantum phase transition. What happens when we now add the bath? That's the question that we want to know. Experimentally, one can do this, and one can cover, in fact, many different regimes of this three-dimensional parameter space. This shows the regimes that are covered by some of the systems that have been looked at in a lot of experiments. And there are others coming now, and of course we can vary the dimension now in quantum optics labs. Okay. So let me start with the iron 8 example, which I discussed for you last time. So this is the great advantage of this system is that it can be made very pure. Lattices of these molecules which have spin 10, and we can apply a transverse field and vary the tunneling amplitude, the effective transverse field, in fascinating ways. So if we apply a transverse field along one direction, we see that the effective transverse field on the system actually goes an Aharonov Bohm oscillations in spin space, and so it actually oscillates from 0 to a finite value and so forth, and then eventually rises up. But if we apply it in a different direction, we just get this. Remember, this is an exponential scale. Here we have a tunneling amplitude or an effective transverse field of 10 to the minus 7 Kelvin. Up here it's 1 Kelvin. Now, there are two regimes of interest. One is where the effect of the bath is so strong that coherent tunneling can never occur. And in that case, we'd simply get quantum relaxation. We get inelastic tunneling occurring. For this system, it turns out that the spin bath is much more important than the phonon bath, and so the dynamics is controlled entirely by the spin bath. So this is actually the analog of a Boltzmann equation for qubits. This is the time, alpha here is either plus or minus, up or down, 0 or 1. And this is the time derivative of the distribution function for the system to be up or down at some position r, and this is the longitudinal field at the site r. And so the relaxation rate is just given by the difference of up and down here. So that would be just a straightforward memoryless relaxation. But then there's this long-range dipolar interaction between these spins, and that brings in the two spin distribution function. Now this can be solved analytically, and it can be solved for different shapes of the system numerically. It can be solved analytically for a system which has an ellipsoidal shape. And various predictions were made for this system, which were in fact verified in many experiments, and they're really quite dramatic. For example, the relaxation rate turns out to be proportional to this tunneling amplitude squared. So in the dynamics, we should see that, and this is a plot in an experiment as a function of transverse field of the relaxation rates for different orientations of the field. It's quite remarkable. But the relaxation rate is also controlled by the nuclear spins, and it turns out that you can calculate what it should be if you know the coupling to the nuclear spins. It goes like delta squared times a function of the nuclear spins, and so if you vary the nuclear isotopes, you should change it. So these are three experiments in which, this is a logarithmic scale for relaxation time, in which we have different isotopes. This is quite remarkable, and immediately convinced the experimental community that actually this was the mechanism. Moreover, it turns out that the behavior over a very wide range of time of the distribution function should go like a square root of time, which is a very unusual scaling law for relaxation. And this shows you the relaxations as a function of real time here. And in fact, they beautifully fit the square root. So this incoherent relaxation dynamics was understood quite early on in this system. And so then the big question was, well, now let's try and go to the coherent regime, which is the one of interest in quantum computation. So the theory for this was done, again, some time ago. And this is where it gets interesting, because now it turns out that by far the most important decoherence mechanism is the one involving long-range interactions. And you see that what we're now dealing with is a three-dimensional analog of that capricious voter model that I showed you. These things are trying to flip. The long-range interactions play a crucial role in the coherent dynamics of this system. And one can actually calculate this mostly analytically for this system. I won't discuss the details, both in low temperature and high temperature regimes. What is crucial, again, is are pairs of spins in resonance. So here we have a plot at a given time for a specific shape of the system. The probability that, a spin at some point will have a local longitudinal field. And you see it varies over the sample for a given sample shape. This is actually, the sample shape is shown here. And the way you should understand this is as follows. Spins where the local field generated by all of the other spins is 0 can flip. This is a plot showing the region in this sample when it's initially polarized where the local field is at this peak. If I now pick the field here, so this is a field, actually a negative field, and this is a positive field, then it's out here. And in fact, what's happening here is that as we shift the field, we can apply a field, you see, to counteract a longitudinal field. We can apply a longitudinal field to counteract the internal field generated by all of these spins, and then put some region of the sample in resonance. And so as we shift the external field, different parts of the sample go into resonance, and those will flip. Of course, once they start flipping, they change the field in the sample, and the relaxation can continue. Now, this is in 3 dimensions, not 2. And the way the experimentalists do this is they just polarize the whole system initially. They lower the temperature, and then they release the field, or they put it to some other value, and they watch to see what happens. They watch the relaxation. And remember, we can adjust this longitudinal field. In fact, we can even scan through this distribution and therefore vary the different parts of the sample that are able to relax. So what they're doing then is looking at but in this case, we're looking where the tunneling amplitude is large, and so the decoherence effects are small, so we should expect to see something. These are the theoretical predictions, and they're very interesting, and I want to look first at this graph. This is the effective transverse field on these spins in Kelvin units, which can be varied by applying an external field. These are the dimensionless decoherence rates. So this is the inverse of the Q factor. So up here we have a decoherence rate of 1. That means that the Q factor is 1, which means the system is critically damped. So obviously no coherence there. Here, it's 10 to the minus 7. That means we have a Q factor of 10 to the 7 for this system. This is the contribution of nuclear spins for one particular set of isotopes to that decoherence. You see how it falls as we increase this transverse field. This is what I explained last time. The nuclear spins can no longer follow the qubits if they're moving really fast. On the other hand, the faster the qubits move, the more they couple to high-energy phonons, so the phonon contribution gets bigger, and this is what I call the coherence window. So this is where you want to go if you want to see real coherence, and according to this, you see a Q factor of about 2 times 10 to the 7. If I change the isotopes, I can raise it to about 10 to the 9, which would be a nice Q factor for a quantum information system. But here's the problem. This is the contribution of correlated errors. It's huge. These are for different temperatures in this system. So these were the theoretical predictions. And we see that we have 3 mechanisms, each of which can be tuned. So these were essentially analytic calculations done for a parallelepiped sample. And then there was a very interesting experimental effort in quite a number of different labs to actually look at this. And they all failed for a period of about 5 years because they couldn't get the fields high enough. And also there were stray mechanisms. But then finally, a group in Santa Barbara, this was the group of Oshalom and Sherwin, succeeded. And they realized that the way they would have to do it would be to take their system to the magnet lab in Florida, where they could apply really big fields. And we got a phone call from them, and they said, okay, we've got the data, but we don't know if it fits the theory because our samples have this very strange shape. So I said, well, send us your shapes, and we'll calculate the answer numerically and send it back to you. But you're not allowed to tell us what your results are. And so that's what happened, and so we sent the numerical calculations back, and they actually had 2 different samples of 2 different shapes, and they applied the fields in various different orientations, so there was a lot of data. And this shows an example of a fit here to the data. So here they kept the field constant, but varied the temperature. The solid lines are the theoretical predictions, actually for 2 different samples, and this is the data for those 2 different samples. The main point is that as you vary the temperature, the contribution of different mechanisms is coming in, and this line here, they call it magnons, but it's actually the correlated error contribution. So you see that it's getting worse and worse as they raise the temperature. So they actually asked us to write the paper with them, which we did, and this is their bullet list of why this was an important experiment. It was the first detection of macroscopic spin precession of qubits, lowest decoherence rate ever seen at that time in spin qubit systems, first measurement of dipole decoherence, which is what I'm calling correlated errors, and first controlled measurement of decoherence rates with all 3 mechanisms. But my feeling was that this was the first observation of correlated errors in a big way, where theory and experiment could be made to fit quantitatively. I should say that just a few weeks ago there was a paper in Nature on another system where they claimed to have found a method of suppressing the correlated errors. And I don't think I agree with that. It's an experimental paper. Okay, here's another example. Again, one that's been studied in many different experiments. So, for those of you who are interested in this, this is a spin 8 system. This is a holmium, which has S equals 6 and, S equals 2 and L equals 6, so the total J is equal to 8. And again, there's purely dipolar coupling between the different holmiums. I'm not going to go through the details of the crystal field analysis, but basically we end up again with a quantum Ising system, and again we can control the transverse term in the Ising model with the external field, and again we have these longitudinal dipolar interactions. So it's the same system as before, but with completely different parameters. The big difference is that in the case of the ion 8, there are 213 different nuclear spins in each molecule, but the couplings of them to the central qubit are actually very small. It's just so you can actually overcome that by applying a strong transverse field. But here, the hyperfine coupling is absolutely colossal. The splitting between each of these different hyperfine levels is actually 1/4 of a Kelvin. And this is because it's a rare earth. And so that means that the hyperfine interaction itself competes with these 2 energies. And in fact, one of the nice things about this system is that I've written it here as holmium X, yttrium 1 minus X. The yttrium has no spin, but its volume is its ionic volume is almost identical with the holmium, so they can simply substitute without changing the lattice structure. And so experiments vary the concentration of the holmium from 1 to 10 to the minus 5. And so they can actually either have very widely spaced ions, disordered of course, or very closely spaced. And it's only when X equals 1, in other words you have a lattice of holmiums as nearest neighbors, that the inter-spin interaction can compete with the hyperfine interaction. Otherwise the hyperfine interaction dominates completely. So we have the very peculiar situation that if we want to get rid of the environment, we have to cool to an energy scale below the hyperfine coupling. Anyway, this system is interesting for many different reasons. It's the canonical experimental system for Ising quantum phase transitions. They've been studying this system for 40 years. And it's also the system that was used it was the first experiments that were done on what was called by the experimentalists quantum annealing, but which computer scientists call adiabatic quantum computation, was actually done on this system in 1999. This is the design now used by D-Wave with superconductors. So here are some of the experiments on this system that are interesting. I'm going to discuss, first of all, these neutron scattering experiments. This was an experiment by the group of Apley and Rosenbaum. The title of their paper says everything that they wanted to say in the paper. It was the effect of a spin bath on quantum phase transitions. So what they argued was that at the quantum phase transition, which is produced by applying a transverse field, as I explained before, you should see the energy of the collective excitations in the system go to zero, a sort of a soft mode transition, which always happens, according to the theory, in a quantum phase transition. Well, it didn't go to zero. It came down. These are the neutron measurements of the collective modes in this system. But as they went through the critical field, it stopped going down and then went up again. And they argued that this was because of the nuclear spin bath, because the energy corresponded with hyperfine energies. I won't discuss this. So this left a big question in the literature. Is it true that a spin bath changes quantum phase transitions? They argued that there was a new universality class. And actually, this is still unsolved. These are experiments done in Grenoble by the group of Bernard Barbara. And here what they did was they simply looked at the hysteresis in a crystal, magnetic hysteresis. And as they changed the longitudinal field, they saw that the rate of relaxation had this extraordinary structure. What you would see in a hysteresis graph would be a series of jumps in the magnetization versus field. And this is showing the derivative of that at some temperature. And this is at another temperature. Oh, sorry, no, I beg your pardon. These are the real and imaginary parts of the dynamic susceptibility, which is basically looking at the same thing. And so they pulled out this structure here. And of course, it turns out that these are nothing but level crossings between the levels that I was showing you on the last slide. In other words, when we apply a longitudinal field to the system to look at hysteresis, all we're doing is shifting these two graphs with respect to each other. Let me explain what this is. This is where you have a spin up qubit, and then if you couple it to the nuclear spin, you spread it into all these levels. The nuclear spin has magnitude 7/2, so we have 8 levels. Now this hyperfine coupling is such that this one here has electronic spin up, nuclear spin down. This has electronic spin down, nuclear spin up. Down. And this one has up. So in other words, the nuclear spin here is down and this one is up. So you can't simply make a transition from here to here. It's blocked because you would have to flip the nuclear spin from state 7/2 to minus 7/2. The only way you can make a transition is going here, where the nuclear spin polarization is the same, and then coming down. So this is why the hyperfine coupling actually blocks transitions. And it explains why the quantum phase transition happens at such high fields in this system. You have to apply an enormous field, transverse field, to overcome this nuclear spin blocking mechanism. But you also see that if you can put them at finite temperature, all of these levels will be populated. So if you have some levels here that are populated, then you can go from here to here, which is much easier. So what they do is they work at finite temperature and they simply scan the longitudinal field, which simply moves these two with respect to each other. And so that's what they saw in the measurements. And they did this both for concentrated and dilute so that they could look at pairwise processes over long ranges. Okay, so that's showing you how actually the kind of time evolution pattern that I was showing you in that capricious voter model can actually be looked at in experiments. And how you see when you have a really big coupling to the nuclear bath, you actually get all sorts of interesting surprises. So if you want to use this lithium-holmium system as a quantum computer, which of course has been discussed by a number of theorists, you actually have to cool to very low temperatures so that the nuclear spins are gone. Okay. We thought it would be interesting to look at a slightly different aspect of this, which is actually rather familiar to atomic physicists. You apply a high-frequency field to the system. Its frequency is much higher than the energy scale of the system, so it's a very, very fast perturbation. And this has been studied for a long time now in NMR. So here's our original Hamiltonian with the transverse field acting on the spins and the longitudinal. This is again the same old quantum Ising system with a coupling to the nuclear spins. But now we add a very high frequency transverse field. And we ask, what will this do? So there's a very well-known formalism for this. When the frequency is really high, you expand in inverse powers of the frequency, the so-called Magnus expansion, and then you can rewrite everything in a time-dependent frame, and this is known as the Fouquet expansion. And so this is what we were doing, and I'm not going to go into the details. But what's interesting is that for high frequency, you end up with a new effective Hamiltonian for the system, which is time independent. And the way you should think of this is you're varying the frequency really fast, so the spins can't follow, but you renormalize everything in the system. And in fact, the new effective Hamiltonian has different Ising couplings, and they're no longer just longitudinal. There's a transverse part as well. So this is the ZZ part, but this is the YY part. And the size of these depends on the frequency. So I can vary their size depending on the frequency. Anyone who's worked with Fouquet expansions will recognize this immediately. So this parameter here is the ratio of the static field to the frequency in appropriate units. And these are Bessel functions. And so you see that in principle I can make one of these couplings 0. So I can, by just applying this high frequency field, completely remove the Ising interaction. And so one goes through the details here. The only one problem we have is, what about the hyperfine interactions? But of course they also are renormalized, and they also, the Y part of the Y and Z part of the hyperfine couplings also acquire this J0 term. So this is interesting. It means that you can take a quantum Ising system and you can alter its phase diagram at will by applying these high frequency fields. And this shows computations for the lithium-holmium system. I won't discuss the algebra. This is the phase. The problem with this phase diagram is that it wasn't well, this is for no AC field in the lithium-holmium system. And you should just look at this. This is the quantum phase transition line as a function of applied field. And this is when you've this has been set up to remove the effects of the hyperfine interaction, but not of the Ising interaction. So what we showed was that you could entirely remove this little cusp here by applying a particular frequency of AC field. And one can go on and look at other aspects of this, the way in which, for example, you can entirely suppress the longitudinal coupling. So in other words, one can actually decouple the spins in principle. There is a certain relation between, people have done experiments in, for example, spins in quantum dots where they apply fields of certain frequency, but it's a slightly different idea. Okay, here's my final example. So I already explained to you how in certain light harvesting molecules, there was this astonishing experimental result, which has been confirmed now in 4 different labs, that you could get coherent propagation of excitons around light harvesting molecules. And the interesting thing is that these are propagating over hundreds of angstroms at room temperature. So this is a caricature of one part of the molecule. These are the subunits, which are called chromophores, which for our purposes can be thought of as 2-level systems. And the exciton is a particle hole excitation, a bound particle hole, which is moving between these different sites. And the astonishing thing is that it moves coherently around these rings. Okay? Actually, in the real system, you have lots of rings which are coupled. and the excitons can even jump between them. And the structure is really a mess. As I mentioned to you last time, the molecular weight of one of these rings is about 10 million. So they're really enormous objects. And the distance from here to here could be 12 nanometers, 120 angstroms. Anyway, I've already shown you the Hamiltonian we'll use. And these really are symmetric. That's wonderful. It means the energy on each site is the same. What happens is that it moves around, and then eventually the energy is transferred to this reaction center where it generates a transition between ATP and ADP, and that's how energy is stored. It's a molecular deformation. And what's interesting now to biologists is whether there's some matching between the decoherence time and the time for this transfer, which would increase the quantum efficiency, because the quantum efficiency of these things is 99%, which is rather astonishing. So these are two articles which discuss a lot of the details. And this is the analytic solution of this model for a spin bath. But then we found a surprise. Because, of course, phonons are very important. The coupling between these excitons and phonons is very important. So what happens? Well, this is a little technical, but the key is that, as I said to you before, there are two kinds of coupling between my particle, my quantum walker, and the bath. There's a coupling when it's on the sites, and there's a coupling on the links. In other words, there's an energy of interaction between a phonon and a charge when it's on some site. But there's also a process when the particle hops from one site to the next, where it can couple to phonons. It can emit or absorb a phonon during the tunneling. So these are called diagonal and non-diagonal processes. And depending on which process you incorporate into the model, you either have what's called the Holstein model or the Piles model. The Piles model is where the non-diagonal processes. Actually, it's sometimes called the SSH model. Suess, Schrieffer, and Higa. Anyway, this is simply the mathematical description of these interactions, which I'm not going to go into, but the surprise was, and amazingly this wasn't known until we did this work, is that the effect of the non-diagonal coupling to phonons is to actually cause a phase transition in the system. And it also, we've discovered that the decoherence caused by the non-diagonal processes was roughly 20 times larger than for the diagonal processes for the same coupling strength. The phase transition is actually a change in the band structure, and this one of these curves shows this. So this shows the band structure as we switch on the coupling, and you see how it alters. It's quite extraordinary. At the same time, when we cross this phase transition, when the band structure changes, actually the effective mass of the hopping object diverges, which is what you would expect. In other words, the particles get frozen. Well, it turns out in these biological systems, the non-diagonal coupling is actually as large or even twice as large as the diagonal one. So in fact, it completely controls the dynamics. Now, the big mystery in these systems, which nobody really knows the answer to right now, is why is decoherence so small in these systems? How is it possible for an exciton at room temperature to move around a molecule like this over distances of hundreds of angstroms? And this is simply not understood. We know it happens because experiments show it, but why? Now, it's possible that this has got something to do with that problem. Okay, so there's lots more to say about this biological example, but it's kind of messy. I just wanted to show you how it's possible to analyze the dynamics of qubit networks, both mathematically and apply it to experiments, sometimes with interesting results. The future of this is rather interesting because what it means is that we should be able to analyze not just one spin or two spin correlations or one particle, two particle correlations, but we should be able to go to n particle correlations, which are of course, or n spin correlations, which of course are what are important in quantum computation. And what these results show is that you can actually calculate those. To measure them will be less easy, but I think that, well, that'll be an interesting problem for the future. Of course, it's crucial for quantum computation. If that is to say, if you want to do real quantum computation and not just adiabatic quantum computation. And I've shown you how this can work for several examples. So that's most of what I'm going to say about conventional environmental decoherence, except I'm going to say one more thing on Monday, which is the next Monday, that is a week from now. I'm going to talk about a mechanism of decoherence that has nothing to do with coupling between environments and system of interest. And we called it was an idea cooked up by myself and Bill Unruh. We call it third-party decoherence, and I'll say a little bit about that. It's where there's no direct interaction to an environment at all. But then most of what I'll talk about in a week from now has got to do with gravity, so a completely different topic. Okay, thank you.